So here we go. Logarithms have been a part of our being, our existence, the processes and manipulations that we've been working with for the better part of the last couple of weeks. So natural logarithms. Now, if we remember back to the very beginning, the way that we defined logarithms, they were the inverses of exponential functions. And when we talked about exponential functions, there was that natural base e, Euler's number. It showed up in our continuously compounded interest formula, and the bare bones function would just be y equals e to the x. Now, the inverse of that function is a natural logarithmic function. We'd write that as now either the log base e of x if we stayed with the manipulations that we had, but being natural log, being log base e, it gets its own special notation. We write it as y equals ln x, ln standing for natural log. Again, natural log being the log base e. So you might ask yourself, well, then what changes? In all honesty, nothing. Natural log is just another log. It's just another log with a base that's not 10, but is almost as standard and more widely used than common log, which is our log base 10. So all of our graphs, they're going to follow all the same patterns and rules that we had for our typical common log functions. All the properties that we talked about, product, quotient, power property, we can apply those to natural logs. And all those equations that we've spent the more recent time solving, we can solve those with a natural log in the same way that we would have solved them with common log or log base, whatever it is that we chose, depending on the problem. So we'll look at the graph. Looks pretty standard as far as logs go. This is the graph of natural log x. Now, it has those same values that we've come to expect from logs. When we defined the values for our regular log, this was the point b1. 1, 0 always existed, and we had the point 1 over b, negative 1. In this case, b is e, and so we get the points 1 over e, negative 1, 1, 0, and e1. Now, any transformations that would have to happen would be about moving those points around. Transformationally, we've got a natural log x minus h plus k, where a still stretches, compresses, and reflects us in the x-axis. H moves us left and right, k moves us up and down. Now, there will be occurrences where that x value will have a negative coefficient. That reflects us over the y-axis, same as it would have any other time. Most other values that are placed in front of there, not just the idea that it's negative, but say it's a 2, properties can manipulate those things out. And then they just get absorbed into a k value, for instance. So our domain, still 0 to infinity. Our range, negative infinity to infinity. Domain is affected by left-right movement. It will also be affected by reflection if we reflect in that vertical axis and the y-axis. Range is completely unaffected by anything. It's infinite in both directions. How about our properties? So we had 3 of them that we really concerned ourselves with, and then there was that other manipulation that we talked about. The first one was our product property. It still holds. The natural log of AB is the natural log of A plus the natural log of B, and it works in both directions. Our quotient property, the natural log of A over B. Well, the natural log of A minus the natural log of B. We still associate a product in an argument with a sum of 2 logs. We still associate a quotient in an argument with a difference of 2 logs. Our power property, what if it's the natural log of A to the n? Well, I can rewrite that as n natural log A. There's no issues there. Those are all manipulations that are completely acceptable. Remember, natural log is just log base e. If I had written log base e, we would never even question that these properties applied because we always wrote log when we used them. ln is just alternative notation that is far more commonly used than log base e. Now, then we had that change of base formula. It's unnecessary. Change of base formula was about us being able to change the base around because log as a function could have any base value that was positive and not equal to 1. Well, natural log is always base e. The need to change base, if we wanted to, we could. But if it's all base e, there isn't really a huge need for it in most cases. Now, the other thing that's nice about that, quite often we were changing base so that we had that button presser ability. Well, natural log is a key on the calculator. We don't need to change bases to be able to put in what we're trying to evaluate. Solving our equations. Don't change anything. Don't think about it differently. Don't understand it any differently. Don't manipulate things any differently. If I'm given an exponential equation, well, as it stands right there, I would be at a standstill. I wouldn't be able to do anything. Change it to log form. Only in this case, log form is going to be the natural log of 2 is equal to 2x. From there, I divide by 2, and x is the natural log of 2 over 2. No big deal. What if it starts out as a logarithmic equation? We manipulate as far as we can, same as we always would have. We'll add 4 to both sides. Well, I'm at a standstill. X is buried inside the argument. The recourse there had always been change it to exponential form. Changing to exponential form. Remember, base is e, so it's e to the 13th is equal to 3x plus 2. I'll subtract 2, I'll divide by 3. X is e to the 13th minus 2 divided by 3. We would put that in the calculator and we would call it a day.